Good evening, everyone. We welcome you all for the IIT JAM online lecture series, which is organized under the DBT Star Strengthening Scheme. We are pleased to welcome Dr. Akshay Kumar, sir, Assistant Professor at the Vellore Institute of Technology, Amravati, Andhra Pradesh. Sir's area of interest lies in functional analysis and its applications to function space. In today's session, Sir will be guiding us through important concepts of linear algebra, a core area for IIT JAM syllabus and foundation for higher studies in mathematics. Let us warmly welcome Dr. Akshay Kumar, sir, and look forward to an enriching session. Over to you, sir.
Thank you, ma'am, for the introduction. So, like, am I able to share my screen? Okay, I am able. Thank you. Thank you for inviting me for this workshop. I hope you will learn something new in this workshop, in this session also. So, I'm sharing my screen. I hope I'm audible to everyone.
Yes.
Okay, thank you. Okay. So today's session is on linear algebra, which is a very important say subject in IT exam. So every year they ask around more than 5 to 6 questions from this subject. So this topic I should say. So before I starting the session, I should recommend some book also. So if you ask me some good books on linear algebra, so some of them are so one of them is Linear Algebra Done Right by Sheldon Exler. Recently, they have published one new edition in 2024, and there is one more book with the similar name called Linear Algebra Done Wrong by some other author. So, but this book is somehow like nice, a very nice book. Then another book is I would say Feedback topic. The name of the book is Linear Algebra, and another one is Hoffman and Kunje. And most of the IITs and the people are following this book only, Hoffman and Kunje. Even when I was doing my masters in at IIT Madras, there also we followed this book only, Hoffman and Kunje. And another book is, of course, by great people, Nair and Arindama Singh. And the name of the book is Linear Algebra. Both are the professor now. That MT Nair is now retired, and actually, both and Arindama Singh is a professor of mathematics in IIT Madras. MT Nair was also a professor at IIT Madras. Now I think he is at Pits Pilani. So I should start. So so the first question is, what is a vector space? So to check a space is a vector space, we actually need some like operations and some set or something like that. So what thing we need? So first thing we need is we need a non-empty set. You can denote that set by capital X or capital V. It's up to you. And with this set, we need a field. If you don't know much about the field, so we usually take in linear algebra, we usually take field is either R or C, real numbers or complex numbers. And we also need two operations. So one operation between the members of the set called vector addition. So suppose X and Y are the members of the set, so this is denoted by this addition. So this is vector addition. This is in between the members of V. And another we need one more operation that is between the, as I said, we need field in the case of to check a space is a vector space or not. So but if you take one member from the field, usually denoted by alpha, beta, something like that, and if you take a member from the set V, so we have one operation. So say dot usually denoted by this dot. So this is alpha dot x. So this operation is in between member of field and member of vector. This set, I should say. Now like once we have all these things, so 1 hour. So suppose we have a set V, this two operations we have, and we have field which is either R or C, which can be either R or C. So this whole thing is said to be a vector space if it satisfies certain properties. So what are those properties? So some properties are related to vector addition. So first property I should say is this operation vector addition is closed. What does this mean? So if you take any two member in the set from the set, then x plus y should be a member of V. So second property, it should satisfy is commutative. What does this mean? So if you have two member, any two member in the set, then this x plus y should be equal to y plus x. This must be held for all the members of the set. And the third property is associative. What does this mean? If you operate x on y plus z, then it should be equal to if you operate y plus x plus y on z. This should hold for all x plus x y z from the set. Now the another property is zero element. What this property says, there exists a member, it is usually denoted by 0, or you can denote by 0v, but it's simply denoted by 0. So you should have a member called 0, this is a notation, belongs to the set v such that 0 plus x is always equals to x plus 0 is equals to x. This whole for all x belongs to the set V. Now the another property, the last property related to the vector addition is the additive inverse. What this property says, if you have any member x belongs to V, then there exists a member. It is usually denoted by minus x. It's simply a notation belongs to V such that x, if you add both the elements, then it should be equal to 0. Yeah. So these properties should satisfy if we are checking for the vector space, right? These properties are related to the vector addition. Now if you observe these properties and if you know the property of a group, so you can say here V plus this with the V with the set V with the operation this plus is forms a abelian group, right? Now there are some more properties related to scalar multiplication. So what are those properties? So first one again, so the scalar multiplication should be closed. What does this mean? If you take any member alpha from the field, it can be either R or C, or an element from the set, then alpha dot x should be a member of the set V. Second property, this is if and then. Second property is, so the scalar multiplication should be associative. So it should be distributive and so first we write distributive. What does this mean? If you operate alpha on beta x, so this should be equals to alpha beta x. So I think this is associative property. This is associative. And this should hold for all alpha beta belongs to the field and x belongs to the set V. And the third property is if you alpha plus alpha into x plus y should be equals to alpha x into plus alpha y. This should hold for all alpha belongs to the field and xy belongs to the vector the set V. And another property is the alpha plus beta dot x is equals to alpha x plus beta x. This addition comes from the field. This is not this addition. This is not this addition. This addition comes from the field. So we know how to add two real number. We know how to add two complex number. This is that addition. And the remaining is 1 dot x equals to should be equals to x for all x belongs to the set V. Right. So these two property called distributive property. And this one is associative. So I have written 10 properties. So if we have a set V with the two operations with a field and if it satisfy all those 10 properties, then this space is called a vector space. Right. So one should ask why we are writing all like too many properties. So actually we are making these operations this addition and scalar multiplication compatible with the elements of this set and members of this field. This is the reason. Means these operations are compatible with all the members of the set V and all the members of the field V. And again, these are also compatible with the operations of the field also. Now, now we should see some example. So the example is if you take suppose if you take r square. So r square is simply xy such that xy both elements are comes from the real number. And if we take our field as say r. Now we have a set. So let's say no, V. We have a set. We have a field. Now we need two operations. Let's define two operations x. So I should write x1 comma x2. Otherwise, like I need many many variables. X1 x2 plus y1 y2. We are defining this as x1 plus x2 y1 plus y2 for all the members of V. This is addition we are defining like this. Now, for if alpha belongs to the field which is R and x is any member of V which looks like x1 comma x2, then we define this operations dot as alpha x1 comma alpha x2. So you can check that now this V satisfy all the 10 properties, so it forms a vector space over the field R. Now what will happen if I change the field? Now you will see the what is like how, means, why the field is important, the importance of the field. Now suppose I change the field. Suppose I take field as the complex number and the set as R square as we defined earlier and the same operations. as we defined in this case, this operation and this operation. So can you tell me, is this a vector space?
No, sir.
No.
No.
Why? What is
Sir,
the reason?
because this scalar multiple will not go to V. Like when we take a
Yeah,
complex
correct.
number from field.
So if you take alpha is equals to iota, so because this alpha called scalars, the members of the field is called scalars, and the members of this V called vectors, right? So if when you take alpha equals to I, the scalar I, and if you take element as 1 comma 0, 1 comma 0, of course it is a member of V. Now if you take alpha dot x, so this is iota into 1 comma 0. So as we defined earlier, so it will be equals to iota comma 0. So this does not belongs to V. So it is not a vector space. That's why the field is very important. If field is real, we generally called, so if our field is real, then we usually called and that V forms a vector space, and V forms a vector space over R, then we call V a real vector space. If field is complex, we call V a complex vector space. Right. Now, so now I should pose a question here. So question is, how, so you must have seen like vectors in your 12th class. Have you seen like
Yes,
Yes.
sir.
the parallelogram and
Yes.
all those things you have seen? So
Yes, sir.
question is, how those, like here we are calling the member of that this set V are vectors, right? There also we have seen vectors, right? So the question you should pose here is how those vectors, so the 12th class you have seen, are related with these vectors. These vector means I am saying R2 with usual addition. This addition, as we define in this case, are called usual addition and usual scalar multiplication, right? So how those vectors are related with these vectors, vectors of R2 over R, right? You should find the answer of this question, and you will see that actually both these things are same. Actually, this is the motivation of vector spaces, and like
Sir,
you should, yeah,
sir, I have like one doubt. We generally define dot from like dot as F cross V to V.
yeah.
Uh, so is it valid if we define dot as from V cross F to V?
No, like
Sir, why? Like, what's the reason?
the reason is if you are defining a function, right? Like you are saying
Yes,
this scalar multiplication is a function from F cross V to V, right? So that means
yes,
you are
sir.
saying it is valid only if first member is coming from the field and the other member is coming from the vector space, right?
Yes, sir.
You can say, like, suppose you take a matrix A, right? This is a matrix, right? And
Yes, sir.
this is a 2 cross 2 matrix. So say 2, 3, 4, 5, right? Now, can you define 2 dot A? 2 means it's a point wise. Like I should not
Yes,
give
sir.
this example at this stage. So, okay. So what is 2 dot A? That is point wise multiplication, right? So you will multiply 2 into
Yes,
2. 2 into 3, 2 into 4, like 2 into 5, right? This is
Yes.
the scalar multiplication you have defined. Is this multiplication
Yes.
is same as A dot B? No, it is not,
No, sir.
right? To
Yes.
define a scalar
Yes.
multiplication, this is actually you are demanding, like the first thing you are demanding that to define a vector space, you need a member from the scalar and a member from the vector space. This is your first statement. Then you will go to the second thing, right? If your
Yes,
first
sir.
thing is not fulfilled, you cannot go to the second thing. This is your you are demanding,
Yes,
like
sir.
this is your first thing. You are demanding that one member comes from the field, another member should come from the V, the vector space or the set V, right? Now, if this
Yes.
condition will fulfilled, right, then you will go to the second thing. It is actually a function, right? You are
Yes,
just
sir.
like if you have a function, so you change the domain every time? It is not always the time. It is actually domain of this function, right?
Yes, sir.
It may not be defined if you
Sir,
change the domain.
can we not can we not define by ourselves that a dot 2 is equal to like pointwise multiplication if we
Yeah, you
define
can
it
define.
in the
So there is a term called algebra. Algebra, which is something more than vector space. So there you will have vector space and one another operation which is between the vector space, members of vector space over a field F. We have this structure that is called algebra. You search about it, you will get all the informations. So here
yes,
we
yes.
have this kind of structure. So
Okay,
that
sir.
is called algebra. That is
Yes, sir.
in that case we define this operation between the this operation there we define usually define V cross V to V. You search about this term
Yes.
algebra. Okay,
Yes.
so let's start again. Okay, so I should give some more example. So if we generalize that R2 example, then suppose n is any natural number, then Rn is, so if we take this Rn as x1, x2, xn, and all these members are from R, and how vector addition is defined? It is defined as pointwise addition, x1 plus y1 xn plus yn, and scalar multiplication is defined as alpha dot x1 xn is defined as alpha x1 alpha xn. So if you can check that this Rn will satisfy all the properties of a vector space and it will form a vector space over R. Okay, these are the finite dimensional vector spaces. Even you can prove that every finite dimensional vector space is actually isomorphic to this Rn for some n. Okay, so I should give some infinite dimensional vector space example. So if you take V as the, okay, I should give some P and R. So this is the collection of all polynomials. So this is R. So real polynomials. If you write P and C, so it will change to complex polynomials. So real polynomials whose degree is at most n. Right. So how to define, like if you write a typical element of V, the here V is P and R, so that element will be of the form a naught plus a1 x plus a n x to the power n, right? And if you write some other element, it will be of the form b naught plus b1 x plus bn x to the power n. And how we are defining vector, how we are taking vector addition? So just pointwise addition, that is a naught plus b naught plus a1 b1 x, like this, an bn x to the power n. Right, this is vector addition. And how we are define scalar multiplication? So a naught a1 x, like this, an x to the power n, and this is equals to alpha a naught plus alpha a1 x plus alpha an x to the power n. And again you can check that this will satisfy all the properties of a vector space, so it will form a vector space, both P and R, P and C. It is a real vector space, it is a complex vector space. Okay, so someone is saying we should include zero polynomials. We always PNR means we usually take all, like whose degree is at most n. This means we are taking zero polynomial in PNR.
But
This
the
is our,
zero polynomial does not have a degree defined.
yeah, but like as I said,
So that is why it has to be specifically mentioned along the side.
that we can write, but usually we PNR means we are taking zero polynomial also.
Yeah. Needs to be mentioned. That's all.
Okay. If you want, you can mention it separately. Otherwise, whenever you will see PNR, either they will write it is a collection of all the polynomials whose degree is at most n, including zero polynomials. Okay, it will form a real vector space and it will form a complex vector space. Now the question is, suppose I am taking W as polynomials whose degree are exactly 2 or something like that. Suppose I am taking W as a set is the collection of all polynomials whose degree are exactly 2, not at most, exactly 2, right? So, and the vector addition and scalar multiplication are the same. And again, we are talking on R. So can you tell me, is this form a vector space or not? So will it form a vector space or not?
No, sir.
Yeah. Why?
Sir, like zero element is not included.
Yeah. So one reason is zero polynomial. So you can write zero polynomial is not belongs to W. And another reason is, suppose, what about the vector addition? Is it closed? Suppose you
No,
have two
sir.
polynomials of degree 2. So what can you say about the sum of those polynomials? So what about, like if you take x square plus 1, and what about minus x square plus 1? If you add both these polynomials, what you will get? Only 2, constant polynomial,
Yes, sir.
right? So
Yes,
it is not a, its degree is not 2. So this will not form a vector space.
yes, sir.
Right. Now suppose I am taking PR. What does this mean? If you take union of all the polynomials union of P and R, n belongs to natural number. And suppose now if you take any two elements, suppose Px and Qx belongs to PR, right? So you can say Px will belongs to Pn R n1, and you can say Qx belongs to Pn2 R, right? So without loss of unity, you can assume that n2 is greater than n1, or you can assume that n1 is greater than n2. It's up to you. So if n2 is greater than n1, then you can say that Px and Qx both are member of Pn2R, right? So this is collection of all polynomials, right? So both member will be in the Pn2R, and we know how to define Px plus Qx. Once they both belongs to the same collection, we know how to define the addition, and we know how to define the scalar multiplication, right? So you can check that
Yes.
this also form a vector space over R. These are actually the classical examples. So you can see these examples in any book. So I'm not going into the proof of all those properties because it takes a lot of time. So now again, one famous example is suppose suppose Y is any non-empty set, right? Now what is F Y R? This is the collection of all functions from Y to R. So this is our set, right? And our field is R, right? Now we need vector addition and scalar multiplication. So suppose F and G are any two member of V. How we will define F plus G? So F plus G at a point X is a member of, or X is a member of, here X is a member of Y. So at point X, this is defined as Fx plus Gx. Okay, so this is for all x, y, x belongs to y, and scalar multiplication is defined as alpha dot alpha into fx. This is a real value. Fx is because this is a f is a function from y to r, right? So fx is a value a value in r. Alpha is a member of r. We know how to multiply two real numbers, right? So this
Yes.
is well defined, right? So you can check that V here, V is a vector space over R. Similarly you can do for the complex number also. There is nothing change in that. Okay, this is also a classical example, and one more example I can give. So say M and R. This is the collection of all n cross n real matrices, right? Or even you can take m cross n also. This will be the collection of all m cross n real matrices, right? And how we will define again, if we write this one, that means we are taking field as R, right? If we take two members A and B, or m cross n m or in this element member. So we define vector addition as, so we can write A as A11, A12, something like that, A21, A22. So this will be, if we are taking n cross n, so this will be n. Right. Similarly, you write B, and how addition is defined. So it will be defined as A11 plus B11, A12 plus B12. Like this, we will define vector addition. This will be A n n plus B n n. Right. Similarly, we can define scalar multiplication like alpha A11, alpha A12, alpha A1n, alpha A1n1, alpha an. Right. So like this, we can define addition and scalar multiplication, and you can check that both these space m n r and m cross n r, both these forms vector space over R. Right. And let me ask you, what is zero vector here? What is our zero vector here? The zero matrix.
Yeah, zero matrix.
So in this case, it is n cross n zero matrix. Right. Okay.
Yes.
Okay. Let me ask you one more question. Suppose our set is V is our R2. Right. And now I'm defining vector addition as x1, x2 plus y1, y2. Like as we defined earlier, x1 plus x2, y1 plus y2. And I'm defining scalar multiplication as alpha x1, x2 is equals to, so let me define like alpha x1 comma 0. Now like when alpha operate on this member, it will make the second entry 0. Right. This is different from the earlier one, and this one is same as the earlier one. Right. The question is V a vector space? Again, I'm asking on R only. Field is R, and vector addition as I defined here, scalar multiplication is this. Now question is it a vector space?
No, sir.
Why?
Because last one times vector equal to same vector,
Yeah.
but there is
So if you multiply a1 x1 comma x2 is equals to, it will be x1 comma 0, right? But the last property says 1 dot x should be equals to x, right? But it is not equals to this element, right? So it is not a vector space, right? Now I can give one more example. Suppose you take v as r square, right? And if you define vector addition as same as the previous one, okay, and okay, we can change this. I can give some. So I'm making it x1 into x2, then y1 plus y2, and alpha dot x1 x2 is same as the usual one. Now, is it a vector space over R?
No, sir.
Why?
Because commutative property is not, it is not holding commutative property. If we do y1, y2 plus x1, x2, it will be y1 into y2, x1 plus x2.
Yeah, correct.
So it's not same.
So if you take 1, 2 plus 2, 3. So with this definition, you will get x1 into x2. So x1 into x2. So 1 into 2, 2. So x1 into x2. And this one is y1 plus y2. So 2 plus 3, 5. Right. Now, if you apply the same operation on 2, 3 and 1, 2, so what you will get? 2 into 3, 6. What is 1 plus 2? 3. Both members are not equal. So R2 with these operations, not a vector space. Okay. Now I should give some example from the real analysis. I think you know many things from the real analysis. So suppose you have C. What is C? Even the collection of all real convergent sequences. C is the collection of all the real convergent sequences, right? And how we are defining the notation is if x is a member of C, so x will be written as a n, right? This is the notation of a sequence, right? So how we are defining vector addition here, the component wise. So an plus bn. Similarly, scalar multiplication is defined as alpha a n, and you can prove that C with these operations forms a vector space over the field R, right? If you take complex sequences, it will form a vector space over C, right? Now,
Yes, sir.
let's move to the subspace. But we can do a lot of interesting things in subspaces. So what is a subspace? Suppose you have a vector space. This is a vector space, right? And W is a subset of V, right? W is a subset of V. If W itself is a vector space, then W is called a subspace of V. Now, as I said, whenever we are checking a set is a vector space or not, we need operations, right? Vector addition, scalar multiplication. So if x and y are two member of W, so how we define x plus y? So
Same
as
as
you
we define.
same as member of V, right?
Yes. Yes.
It is same as x plus y in V, right? So whenever we are saying W is a subspace of V, so W is a vector space, W is a subset of V, and operations, vector addition, scalar multiplication, field, everything is same as we have, right?
Yes.
Okay. So the question is, suppose I'm taking W as C naught naught, right? Okay, I should give one property, so you can mark it as theorem. So suppose V is a vector space, you don't need to like when you are checking, whenever you are checking W is a subspace or not, you don't need to check all those 10 properties. So we only need to check only two properties. What are those properties? Suppose V is a vector space and W is a subset of V, right? Then W forms a subspace if and only if these two properties should satisfy. First one is zero member. This zero member is the zero member of V. Now this member should belongs to W, right? Second property is if X and Y are any two member of W and alpha is a member of field, then this alpha X plus Y should belongs to W. If these two properties are satisfied, then W will be a subspace of V. Now, even you can prove that this property is actually equivalent to the vector addition is closed and scalar multiplication is closed. So instead of writing two different properties, we have made them into one property. So this is nothing but the we are writing vector addition is closed and scalar multiplication is closed. Okay, so I should give some example. Suppose you have V as R2, your vector space over R, and I am saying W as X comma 0, where X is member of R. Of course, it is a subset of V. And the question is it a subspace? Is it a subspace?
Yes, sir.
Yes, it is a subspace. So it is a subspace. So this is a subspace. You can check this property. It is very easy to verify. Again, suppose this is W1, so W2, 0 comma X, so that X belongs to R. This is also subset of V. V is R2. Now, is it a subspace?
Yes, sir.
Yes.
This is also a subspace of V. V is our R2. So if you observe that, so this is nothing but x-axis, right? So suppose you have, this is your
Yes, sir.
R2, this is your x-axis, this is your y-axis, right? Now, so this is your x-axis, right? First one. So you are saying this x-axis is a subspace of R2, right? And the second one is your y-axis, right? So this
Yes,
is
sir.
your y, this is also a subspace of R2. So like one should ask here is, so these are two lines, right? This is x-axis line, this is y-axis line. So if I draw any line here, any line, so this line, so say line L. So is it a subspace of R2?
No, sir.
Yes.
No. Why?
So because zero element is not there.
Yeah, because zero element is not there. Right? Now, if we add zero element in this, then suppose I'm taking this line, any line which passes through the origin, right? This is our zero element, right? Is it a subspace?
Yes, sir.
Right. So it is a
Yes, sir.
subspace. So you can see, you can check that what are the subspaces of R2. Always, like 0 is always a subspace of a vector space. So 0 is a subspace of R2, right? Second one, we have seen that
Yes.
every line which passes through origin is a subspace,
Subs.
right? And you can
Yes.
check that the only remaining subspace is R2 itself. A vector space is always a subspace of itself. Okay.
Yes.
Similarly,
Sir,
you can.
I have a question. You draw any line which does not pass to 0. So
Yeah.
that line along with 0 element, if we add a 0 element in the set of all the points of this line, then will it make a subspace?
No, it will not. The reason is, suppose you take any element here, right? What is the, you can say this is say x1 comma 0, right?
Yes, sir.
Now, if you take 1 by 2 into x1 comma 0, where it will be? Somewhere here,
Yes, sir.
right?
So,
So it is
yes,
not in the line.
yeah, it is not in the.
And if this point belongs to that line, then that line will be x-axis only. If you take any line which passes through, straight line passes through this point and this point, so it is the only x-axis,
Yes, sir.
right?
Yes, yes, sir.
And if you check for R3, the only subspaces are the 0 subspace, line passes through origin, and third one is, now in you are in R3, 3 dimension, so you can have plane also. Plane passes through origin, and another R3 itself. These are the possible subspaces of R3, right? Now I should ask this question, that suppose you have this R2, right? And we have just seen that this x-axis, this line L1 you can say, and this y-axis, this you can say line L2, right? So x-axis, this L1 is a subspace of R2, right? L2 is also a subspace of R2, right? Now my question is, what will happen if we take union of both these lines? Is it a vector space? Is it a
No, sir.
subspace of R2?
No, sir.
Why?
Yes, sir.
So if you take 1 comma 0 and 0 comma 1, it is not closed.
Sir, will the x-axis and y-axis will be a subspace in this part? Yeah, both x-axis and y-axis are the subspaces of R2. I just mentioned here both these subspace of R2, subspace of R2. Okay, so I was asking that this is may not be a subspace. Why? So if you take this point 1 comma 0 here, and if you take 0 comma 1 here, right? So if you add both these points, you will get this point 1 comma 1, which is not in the x-axis on and y-axis, right? So here you can note that union of two subspaces may not form a subspace, right? And even you can prove this result that what about the intersection? Intersection
It,
always form a vector, always form a subspace. So arbitrary intersection It doesn't matter you are taking 2 or 3 or how many you are taking. Arbitrary intersection of subspaces of a vector space again form a say subspace. It's not easy to, it's not hard to prove this. Now I was asking about the union. So now the question is, when suppose you have two subspace W1 and W2 and you take union of this. When this union, I'm talking about the arbitrary vector space, not about the R2. Suppose you have a vector space V and W1, W2 are subspaces of V. So when the W1 union W2 forms a vector space.
See,
Either
if
W
is a subset of W2 or W2 is subset of W1.
Yeah, correct. So either W1 subset of W2 or W2 subset of W1. So even this is a result that W1 union W2 forms a vector space, forms a subspace if and only if either W1 subset of W2 or W2 subset of W1. Correct. Okay. Now, like, we can solve some previous year questions from the subspaces. So I have some questions. Okay. So the first question they asked in 2024. Suppose W is a subspace of a non-zero vector space. Again, okay. So for a subspace W, W is a subspace of V. V is a non-zero vector space. And whenever you have a member U from V minus W, and you have a member V from V minus W, so will U plus V a member of V minus W? What you can say about this? So what this question is saying, suppose you take a member U outside the subspace, right? And you are again taking another member, another element from outside the subspace, right? It is like this is your vector space, this is your subspace. Here, this is your member U, this is your member V, right? What you can say about V plus the U plus V?
Sir, it's a false statement, right?
Why?
Sir, if we take like W as y-axis
Okay,
and
can you tell me simpler than that, than this?
Sir, can I?
x minus x will be 0. So,
You just take U equals to 0 and V equals to 0. Okay, sorry. So it should be V minus
sir,
Yeah,
W. Okay,
sir,
sorry.
sir, can I say?
Yeah.
Sir, if we take U plus V, sometime contradictory, it is belongs to the W. Okay. Then, then U already taken outside. Then, if we consider U plus V minus U. Okay.
See, whenever you prove a statement false, you have to give an example,
yes.
right? You cannot like here you cannot prove that this statement is always false. It may happen that U plus V belongs to W. The question is asking whether it will always happen.
No, sir.
No.
Sir,
So
if we
as
vector
someone was saying,
yeah,
if you take R2 something, someone was saying.
So we can
if we
find
take
a counter example, then we can
Yeah,
disprove this one.
I'm asking for the example only.
Sir, in
sir
x-axis
R2
and
is
x-axis and y-axis is a vector space,
Okay.
and we take -1 is outside from x and y axis, and another one is 1, 1 is outside from both of these vector spaces. Then if you add, this is inside the subspace.
What is your U?
So U is -1, -1.
-1, -1. So maybe it is here. Okay.
And
Another one
another
is
is 1, 1.
okay, 1, 1. Okay, okay. If you correct. If you take I was I was about to tell you this. What about if you take v equals to -u,
Yes, sir.
right? And if you add them, u minus u plus v equals to u minus u plus minus u, you will get zero element, and zero always belongs to the subspace. So zero not
Yes.
belongs to v minus w.
Sir, but
Right.
we
You take
cannot take
any
like,
non you take any, since it's a non-zero sub vector space, you take any non-zero element, right?
yes.
And if you
Sir,
take
but
v equals to minus u, yeah,
sir, here like x-axis and y-axis is not a subspace, no?
x-axis and y-axis are
Like,
always subspaces.
so then we have to take only one, like either x-axis or y-axis.
You can take whatever you want. Like if you are taking w equals to x-axis, then it is fine. If you are taking w equals to y-axis, then it is also fine. It's up to you. You
Yes, sir.
don't yeah,
Because here
you
I
should
think we have taken, you
you
only have
cannot
to,
take both at a time. Either you have to take w equals
yes,
to x-axis or y equals to w equals to y-axis. You cannot take both at a time.
yes, sir. Yes, sir. Yes, sir.
So I think he was saying that you just take x-axis, and now you take this one element, and if you take this minus, so -1, and if you take 1 comma, or like maybe he was saying so something, if you take -1, and if you take -1, 1. If you add both the elements, you will get -2, 0. So it is in x-axis, belongs to, if you take w equals to x-axis, it is belongs to w, right? So it is belongs to w, and both the members are not in w.
Yes, sir.
So maybe he was saying this.
Okay,
Okay,
sir. Yes, sir.
and simply you can check, if you take v equals to -u, then u plus v, of course, will be a member of w. So it will not be a member of v minus w. Correct? Okay. Now
Yes, sir.
my question is this statement always false? Is it always we have just seen that this statement is false. Now my question is it always false? Can you give an example in which this statement is true?
Sir, I think it will be always false.
See a
Okay.
Because
zero
suppose,
vector space if we consider zero.
Yeah, correct. You can you just consider this zero subspace.
But sir, it is non-zero vector
No,
space.
non-zero vector space. This is non-zero vector space. We have nothing about W. And even if you take non-zero subspace, okay, I'm taking non-zero. Okay, then what can you say about this?
Sir, it will be false.
Always.
sir, I think we can take the example you gave, u and minus u, and
Okay,
then I
okay,
can
okay. Think about it.
always.
So suppose you take W equals to x-axis, right? Now take
Yes,
this
sir.
number 1, 1. So 1, 1.
Yes,
If you take u equals to 1, 1, right?
yes, sir.
And if you take
Yes.
v equals to u, then
Yes, sir.
what about u plus v? Is it a member
It
of
will not
W?
belong.
Huh?
No, sir.
No, sir, it is.
So it is not belongs to W. So it will belongs to V minus W.
Yes,
So
sir.
it is not always false.
Yes, sir.
Please repeat once.
Okay. So if you take W equals to x-axis, right? So it is a subspace of R2, right? Now if you take U equals to this member 1, 1, so U is not a member of W, right? So U is belongs to V minus W. If U is not belongs to W, that means it has to belongs to U minus W, right?
Yeah.
If you take V equals to U, so what is U plus V? This is 1, 1 plus 1, 1. So in total you will get 2, 2. So is this point on x-axis?
Mhm.
No.
No.
So it is not a member of W. So it has to be a member of V minus W, right? So we have an example which shows that this statement is false. We have an example which shows that this statement may be true. So it is not always false. It depends on your subspace, what subspace you are taking. Right.
Yes.
So in 2023 they asked about this question. So which of the following is a subspace of the real vector space R cube? So since we are talking about real vector space, so our field is R. We are doing everything on R only. Okay.
Sir.
So immediately after looking at the option, can you tell me why this D is not a vector space? This one.
Because
Why
zero does not belong.
zero member is not there?
It does not pass through like the origin.
Yeah. And the meaning of that is zero member does not belong to this set. If you put x equals to 0, y equals to 0, z equals to 0, it doesn't satisfy this equation,
Yes,
right?
sir.
So it is not a subspace. Okay. Now can you tell me about the B option? Why it is not a subspace?
Sir, uh, sir, if the
Okay. Can
field
you take
is
this example? Can you take
scalar
this example?
multiplication is not used.
B option, you just take a member. So suppose my member is say 1, 1, 1. This is a member of this. So let's denote this by W. So it is a member of W.
Yes, sir.
What will happen if I multiply this by root 2?
So then it wouldn't be because of rational.
Yeah, it will be root 2, root 2, root 2,
So this does not belong to.
It won't be
right?
Yeah,
And
so it is
root
not.
2 does not belongs to rational.
rational number.
Yeah,
Yes,
so it is not a subspace.
yes.
Okay. So what can you say about this option, C option?
Sir, it will be x-axis because yz plane is 0.
No, it is not an x-axis.
So this is a plane, sir.
So plane yz is 0. Sir.
Okay, let me take two elements here. So what can you say about this element? So 0. So yz equals to 0. So what we need to check, vector addition. Okay. So 1 minus 1,
Sir, this means that at
0.
least
Okay.
one of
Okay.
z should be 0,
So
right?
if you take this member 1 minus 1, 0, is it a member of this W?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay. If you take this member, is it a member of W?
Yes.
Yes, sir.
If you
Yes.
add
But
both,
addition is
if you add both the members, what will you get?
yeah, it is
2
not 1
It is
minus
minus
1,
1
not
1.
1.
belong.
So
It
is
will
it a
not
member
belong
of?
Yes,
to
sir.
the
It will not belong to.
So it is not a subspace.
Subspace.
Right. The only remaining option is this. Right.
Option
So
A.
why this option is correct? So if you see this, so I should add one page here. Okay. So the equation is y plus z square plus 2x minus 3y square equals to 0. Right. So suppose I have two numbers. Suppose alpha square plus beta square equals to 0. So what can you say about alpha and beta?
Both has to be 0.
Yeah, because square of a number is always a non-negative quantity. It is a non-negative quantity.
Yes.
It is also a non-negative quantity, and you are saying sum of these two quantities are 0. So both quantities has to be 0 only,
Yes.
right? So from this equation, what you can say, y plus z is square is 0 and 2x minus 3y square is 0, right? From this, what you can say, y plus z is 0, even if and only if, right? And this is if and only if
Yes.
2x minus 3y equals to 0, right? Now if you
Yes.
write w1 as, so x, y, z such that y plus z equals to 0. So it is a vector space. It is a subspace of R3, line passing through the origin. If you take w2 as x, y, z such that 2x minus 3y equals to 0, again it is a subspace of R3, right? Correct?
Yes, sir.
Now what is your w? This w. This w says a member belongs to w if and only if these two conditions satisfy. This condition satisfy, right? And we are saying this condition will satisfy if and only if these two conditions will satisfy, right? This one, right? And
Yes.
we are also saying these two conditions will satisfy if and only if these two conditions will satisfy, right? So what
Yes.
is w actually? W is actually w1 intersection w2,
Yes, sir.
Yes, sir.
Yes,
right? So intersection of
Yes.
subspaces is always a subspace,
Subspace. Subspace.
right?
Yes,
So
sir.
Yes, sir.
W is a subspace. So since we are running out of time, I should close this by asking one question. So it is, you can say, one of my favorite question from linear algebra. So if like suppose you have two subspaces, W1 is a subspace of V and W2 is again subspace of V. Right. It is my one of the favorite question from the vector space part, not beyond that, only subspaces. So suppose I'm saying if you know about the addition of two vector spaces and direct sum. So since I have not discussed about these things, still I'm asking this question. So suppose you write W1 intersection W2, and I'm saying W3 is also a subspace of V, right? And I'm saying this is also, do you know about the, do you know the meaning of this? We will discuss this later.
Linear
yes, sir.
direct sum, right?
Direct
Yes,
The
sum.
sir.
symmetric difference.
So since we are closing this session, that's why I'm asking this question. If you don't know about these things, don't worry, we will discuss this later. So I'm saying V is equals to W1 direct sum W2. And I'm also saying W1 is, V is also equals to W1 direct sum W3. Like the first part is same,
Yes.
right? The question is, what can you say about W2 and W3?
So they might be same.
So think about it. Maybe like you need to find some examples, or maybe you need to prove this. But it
Yes.
is actually an interesting question.
Okay, sir.
Okay.
Okay. Okay. In next session, we will find either we will prove this or we will find an example for this. With this,
Yes.
let me close this session.
Participants, if there are no more questions, in fact, I would suggest to keep your questions for the next session, or as sir has already given you the email ID, you can post your suggestions and your doubts to sir. Thank you very much, sir. And we look forward to your next sessions. Thank you, participants.
Thank you.
Yeah.
So can I leave the meeting?
Yes, sir. Yeah.
Thank you,
very
sir.
much.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you. Thank you.
Thank you, sir.
Thank you, sir. Thank you, sir.